Hello teachers, let's talk about Chapter 5 Integers, and this time we're going to discuss Section 5.2, Multiplication and Division of Integers. Remember we discussed Section 5-1 last time, which is addition and subtraction of integers. And in this section we're going to talk about models for multiplication of integers, properties of multiplication of integers. We are going to talk about integer division. Then we're going to talk about the last one, inequalities with integers. And then finally at the end, I know these are out of order, order of operations on integers. Now I want to show you the chip model here. We've got 3 groups of 2 red chips. What this is actually modeling is multiplication, and it's going to be 3 times negative 2. And you'll notice we have 3 groups, what the 3 represents here, of negative 2. And we can see that the answer to that is negative 6. So that's our first multiplication problem. Now next we want to model negative 3 times negative 2, and that can be just a touch confusing. Whenever you see the negative in front, what we're talking about here is removal. So we need to remove whenever you see that negative in front. Now, we have to build something where we do have those values to remove. So we just start off by putting both positive and negative. Remember, those cancel each other out. So we're building 0 right off the bat. And we need at least 6 of them to model this particular problem. You could actually put more than 6 if you wanted to here, but 6 is plenty to model this problem. Now, if you'll notice, we're modeling 3 negative 2's, okay? Not negative 3 negative 2's, okay? The negative, again, is going to be the removal. So whenever you see the negative in front, that's remove. So that represents the negative. And then we have 3 groups of negative 2. So the 3 groups is positive 3, and the negative 2 is the chips inside. So we got negative 2, negative 2, negative 2. Now again, that negative in front means removal. So we remove all the red ones because that's 3 groups of negative 2. And then we're left with the positive 6 result. Now, we need to be able to understand the number line model as well. So something you can do is go back to your cat. Demonstrate multiplication by using a cat moving along the number line. You remember the rules for walking on a number line? You always start at 0 and always face the positive, which is the right direction. If the number is positive, you walk forward. If the number is negative, you walk backward. That's the rules that we had before. We turned around only when we were subtracting. And then again, positive, you walk forward. Negative, you walk backwards. All right, so let's take a look at multiplication with our cat. And notice what's not included in this picture is what we're actually modeling. So I want us to talk about it to see if we can figure it out. So we have a negative 3 and then another negative 3. So that appears to be 2 times negative 3. And we know that 2 times negative 3 gives us a value of negative 6. Now what about the second situation? Notice we still have 2 times negative 3, but it talks about the opposite of negative 6 is 6. What we're actually modeling here is negative 2 times negative 3. So what you do on your picture is you still set up the 2 times negative 3, which is tail to tail, 2 negative 3's. Again, backwards, the cat's walking backwards because we're going in the negative direction. But this negative in front, that is your opposite. Just like you remove charges from your circle that's modeled whenever you have the negative in front, on the number line, you take the opposite of that value. So negative of 2 times negative 3, or you could read that as the opposite of 2 times negative 3. would equal the opposite of negative 6, which is actually positive 6. Now we could also try to build a pattern model to come up with the answer. Our ultimate goal still is the strange problem of handling negative 3 times negative 2. Now my favorite way is to consider this is the opposite of positive 3 times negative 2. And then a positive 3 times negative 2, remember we just have 3 groups of negative 2, which would be negative 2 plus negative 2 plus negative 2, which is actually written right here, and we know by addition of integers that that answer is negative 6. You could also use the commutative property. If we know that negative 2 times 3 is the same as 3 times negative 2, and that's negative 6. Now we could build a pattern. So we know 3 times negative 2 is negative 6. That means 2 negative 2's is negative 4. 1 negative 2 is negative 2. 0 negative 2's is 0. So notice the pattern. We're just really adding 2. And what's happening over here is 3, 2, 1, 0. Now it's negative 1 times negative 2 must be 2 if we keep adding 2. Negative 2 times negative 2 must be 4. And finally, negative 3 times negative 2 must be 6. And that's a different idea than what I have written here and what we did when we modeled with the chip model, or what we did when we took a look at the number line. Again, I think my favorite and maybe the easiest to possibly understand is dealing with the opposite. So when the opposite, you take the opposite sign of 3 times negative 2. And we already knew how to handle 3 negative 2's, and then, again, like we said, take the opposite. Now we have a definition here of integer multiplication. We're going to let A and B be any integers. If A is greater than 0 and B is greater than 0, then A and B are whole numbers with a product AB. In other words, we already know how to multiply two whole numbers together. If A is less than 0 and B is less than 0, so they're both negative, then AB is equal to the absolute value of A times the absolute value of B. So for instance, if we multiply, hey, let's just do the problem we just did, right? Negative 3 times negative 2, we would take the absolute value of negative 3 times the absolute value of negative 2, which is really just 3 times 2, which gives us 6. So that's even another way to handle negative 3 times negative 2. But this is actually a definition rather than a model to explain why it's true. See if one of A or B is less than 0 while the other is greater than 0, then notice A times B is negative. So basically when the signs match and you multiply, if the signs match, the answer is positive. And if the signs are opposite, or if they're different, the answer is negative. Well, multiplication has properties as well. As you can imagine, we've talked about properties every time we introduce a new operation. So for all integers, A, B, C, that are elements of the integers, in other words, integers A, B, C, closure property of multiplication of integers. So A times B is always another integer. In other words, multiplication in the integers is closed in the integers. You're never going to get an answer that's not an integer. Commutative property of multiplication of integers, A times B is always equal to B times A. And then we have the associative property of multiplication of integers. If you group together A, B, and multiply that first and take that answer times C, it's the same result as if you multiply B, C together first and multiply A times that result. We have a theorem here we should talk about as well. If we multiply negative 1 times any integer, the result is going to be negative of that integer. If you multiply negative A times B, that's going to be the same result as B times negative A, which you pull the negative out front, which is just negative of AB. And then finally, number 3, I feel like we've discussed before already when we talked about the definition of multiplication, but negative a times negative b is just ab. Then we have a distributive property of multiplication over subtraction. So if you need to multiply a times parentheses b minus c, that's going to give you AB minus AC, and you could also multiply from the back. So the A times B, we could write that as BA minus CA. You could always commute these though, and it would be AB minus AC. That's perfectly okay to do. So we're supposed to simplify each of the following so there are no parentheses in the final answer. What I'm going to do first is do like we did in the last section. We have negative 3, and I'm going to change my subtraction to addition, and then change the sign of the next number by using the definition of subtraction, and then distribute over addition. So it'd be negative 3 times x, and then plus, then we have negative 3 times negative 2. And then when I simplify that, that's negative 3x, and that's going to be plus negative 3 times negative 2 is 6. And that's completely simplified. Another way that could be handled is if we distribute over subtraction. So I can multiply negative 3 times x and then multiply the negative 3 times the 2 and bring the subtraction down. So watch this. So we have negative 3 times x, bring down the subtraction, and then we have negative 3 times. Now the subtraction has already come down, so that's going to be times 2. And then when I simplify, that gives me negative 3x, and then minus, now negative 3 times 2 is negative 6. But then we have a subtraction and a negative, which is going to simplify to negative 3x plus 6. Notice we got the same answer. It's really which way you feel more comfortable with. The second, when you just distribute over subtraction, might be a little faster. It really, again, depends on which way you feel more comfortable, and you need to be able to see it both ways to help out your students. Now, if you'll take a look at the typed up version, they distributed over the negative. So we have negative 3 times x. Right here, we bring down the subtraction that's here. Negative 3 times 2 is written next, which is negative 3x minus a negative 6. And then when you have that subtract and negative, that's the same as addition. So negative 3x plus 6. Let's try example B. Okay, so we're going to distribute, again, across subtraction. Let's don't do this one two ways just to avoid a little bit of confusion. So I'm going to distribute the entire x plus 4 times x, and then once again times 4. So that's going to be x plus 4 times x, bring down the subtraction, and then x plus 4 times 4. Now we have that distributive property where we can multiply here. So we can say x times x is x squared, x times 4, or 4 times x is 4x. Bring down the minus. Okay, 4 times x is 4x, plus 4 times 4 is 16. Now we need to run this negative through. It's like a distributive property. It gives me x squared plus 4x. I'm going to be minusing 4x, but I'm also going to be minusing 16. Now the 4x and the negative 4x cancel, and I'm left with x squared minus 16. Now just to recap, let's look at the typed up version of that. So again, notice that we are distributing this front x plus 4 inside. Trying to highlight it. There we go. So that it's here and here. It's times the x and then times the 4. The subtraction just moved over to the middle. And then we distribute. So x times x and 4 times x, and then 4 times x and 4 times 4. The minus comes down, but then it has to plus a negative run inside. So that's negative 4x plus a negative 16. The 4x's cancel. One's positive, one's negative, and we're left with x squared minus 16. The fact is, that has a special name. It's called the difference of squares formula, and typically we use it in reverse. In other words, we are given the a squared minus b squared, and we have to write that in factored form. So we call this factored as a plus b times a minus b. And here we have an example. They want us to use the difference of squares formula to simplify the following. Now let's go back and look at the formula and make sure we understand. So notice we have the same values first. A is the first in both positions, and then the same values in the second position, where one of the factors is plus and one of the factors is minus. Now look at the result. It's the first one squared and the second one squared with a minus in the middle. Okay, so let's apply that. So 4 is in the first position of both. B is in the second position of both. Again, there's a plus and a minus, which means that we would have the first one squared minus the second term squared. We know 4 squared is 16, minus b squared is b squared. And that is completely simplified. If I show you the typed up version, notice how they just rewrote it. They squared the first one, they squared the second one, and then they subtracted. Now let's look at the next problem. Okay, so we've got negative 4 in both first positions, b in both of the second positions, one addition, one subtraction. So it is in the right form. You've got to make sure you're in the correct form before you do this. So my answer is supposed to be the first one squared. So that is negative 4 squared with a minus, and then the second one squared. Okay, we know negative 4 squared, that's negative 4 times negative 4, which is a positive 16, minus b squared, and simplified. Notice I get the same result for both of these. And let's look at the typed up version. And notice that was solved exactly the way that we just did it together. Now, let's talk about factoring. When the distributive property of multiplication over subtraction is written in reverse order, is AB minus AC, and then notice the common A is pulled out front. So that A and that A is pulled out front right there. And then notice what you're left with, which is B minus C right here. Okay, and then BA minus CA, again, notice what's common to both of those is the A that happens to be written in the back, and that is that A, and then what's remaining is the B minus C, which is right here. Okay, so that is called factoring. You often see it called factor the greatest common factor. And similarly for addition, the expression on the right of each equation are in factored form. The common factor A has been factored out. Both the difference of squares formula and the distributive properties of multiplication over addition and subtraction can be used for factoring. So you'll see whenever you're asked to factor, sometimes the problems are in the form of difference of squares, and sometimes it's the distributive property of multiplication over addition or subtraction. And again, difference of squares is a commonly used term. And then down here, greatest common factor is a commonly used term here. Now, we use greatest common factor when we're trying to find a number that the highest number that divided into 2 or more whole numbers. Well, that applies in terms of factoring too. It's the same idea. Now, we're supposed to factor each of these completely. When you factor, you need to recognize the pattern. Remember, we've covered 2 different methods, difference of squares and the distributive property. So here we go. If you look at the first one, the difference of squares only applies when you have a subtraction problem, which we definitely do, and x squared is a perfect square, and so is 9. So when you factor using a difference of squares, you have two sets of parentheses with one plus and one minus. And remember, the same number goes in the first position. So we've got to imagine, what would we put in the first position that if we squared it, it would give me x squared. Well, that must be x, right? And then the same situation here. What number goes in the second position that if we squared it, we would get 9? Well, think about what number squared gives me 9. That is 3. And this is factored completely. And there it is typed up for you. Now let's try this again. Okay, now it turns out that the problem we have here is another difference of squares. It looks a little different, right? But this value is a perfect square. This value is a perfect square, so it's something squared, and we have the required subtraction. So if we factor this into our two sets of parentheses, notice I'm making them a little wider than before. What goes in the first position is what makes the first thing squared. So it's going to be x plus y in the first position on both factors. What goes in the second position is what makes z squared, and that's going to be z in both of those. And then finally, remember, we need, just like here, we need one plus and one minus. We need a plus and a minus. And that is completely factored. And you'll see that's exactly what we have here. Now the last problem, or C, maybe not the last problem, but C is not a difference of squares at all, okay? But notice there is a greatest common factor, and there's an x to both of these. So we're going to use the distributive property in reverse and pull out that x. So if that x comes out front, what's left here is going to be negative 3. And then plus 5y. And there is your typed up version, x times negative 3 plus 5y. Now let's spend a little bit of time talking about division. And we want to talk about the chip model, which might be ever so slightly confusing. But notice in this first picture here, in the first chip model, we're trying to model negative 15 divided by 3. So if we start with negative 15, so that's going to be, notice we've got 15 negatives inside the circle, and we're trying to split that up into 3 separate partitions. So if we start divvying these out into 3 separate partitions, notice we're going to have the same amount in each one. It's going to be 1, 2, 3, 4, 5 negatives in each one. So we could say negative 15 divided by 3 must equal negative 5. Now on the other hand, imagine how we're going to do this. If we were doing the second example, you see at the top is negative 10 divided by negative 5. All right, so we could start with negative 10, so 10 negative chips. But if we were dividing by 5, we would just have 5 partitions down here, and we would split the answer into each one. Okay, but because we're dividing by negative 5, instead of having 5 partitions, we can't do that, right? So we're going to group negative 5 inside, and the actual answer is how many groups you have. So the negative is going to go with the chips, and you're going to use the groups. So you've got to think about that for a minute. You've got to get that stuck in your head. It's a little bit of a confusing situation. So again, if you're dividing by a positive, that's your partitions. That's how many groups you have. If you're dividing by a negative, that's going to have to represent your chips, and you're going to need to determine the number of groups that you have from that. Now, what probably is easier to understand, for all integers a and b, a divided by b is a unique integer c if it exists, such that a is equal to b times c. That's actually what you're really doing. So for instance, if we say, let's don't deal with negative numbers right now, if we just say that 10 divided by 2 equals what number? Well, what you're really finding is that 10 is equal to 2 times what number? Of course, we knew the answer was 5, but when you first started learning division, this is probably the way that you thought about it. What do you multiply 2 by to make it into a 5? And you had just learned your multiplication facts, and now you're using them to work in reverse. So we're supposed to use the definition of integer division, if possible, to evaluate each of the following. So 12 divided by negative 4. Now you may know the answer to that, but what we're supposed to consider is that, let's just say 12 divided by negative 4 equals c. Then if we use our definition, then we could say 12 is equal to negative 4 times c. Now what would c need to be for that to happen? C would be negative 3, which means my answer to this problem is negative 3. And you look at the typed up version of that. Again, let 12 divided by negative 4 equals c. Then you could say by definition 12 is equal to negative 4 times c. C would have to be negative 3 for that to work. Therefore, 12 divided by negative 4 is negative 3. How about you do me a favor and pause the video and you do the next one. All right, now you can look above and say, okay, let's do it exactly like them. Let negative 12 divided by 4 equal c. Then we can say negative 12 is equal to 4 times c. Now what would c need to be such that 4 times that thing equals to negative 12? Well, c would have to equal negative 3. That means you can say that negative 12 divided by 4 is equal to negative 3. And again, the typed up version of that is exactly what we just said. And there you go. Now I have more examples for you. I have a C and a D where you're requested to do exactly the same thing. Again, please pause the video, do those two to make sure you understand the definition, and then we'll do them together. All right, so once again, we've got let negative 12 divided by negative 4. Let that equal to C. Well, what that means is negative 12 is equal to negative 4 times C. Now, what would C need to be to make that true? Well, how about a positive 3? We know this from our rules for multiplication. And what I can say here is that negative 12 divided by negative 4 is equal to 3. Now, what you'll notice, especially if you look at all these, we'll make our rules in just a minute. All right, here we go again. So you take a look at this one too. So negative 12 divided by 5, let that equal to C. That means negative 12 would equal to 5 times C. And then you might look at that for a minute and go, well, C is going to have to be some kind of fraction, right? But we are doing this division within the integers. There is not a value of C that makes this true. So C is what we call undefined in the integers, Ni. We can't do this problem. Now, that doesn't mean forever we can't do this problem. When we're introduced to fractions, we should be able to do this problem. But right now, we're talking about only integers. Now, you know what this means? This means division is not closed in the integers, whereas addition and multiplication and even subtraction are closed, division is not. Now let's look at our results. That is the result that we got before. I forgot to flip to the results page. And look at the result for negative 12 divided by 5. Because no integer c exists to satisfy this equation, negative 12 divided by 5 is undefined over the set of integers. And therefore, integer division is not closed in the integers. Still not finished. We've got AB divided by B such that B is not 0. Why do you think they put B is not equal to 0? Well, when you're dealing with a variable, we don't know what the value of B is, but we know we're never allowed to divide by 0. That gives us an undefined result. Now, if we use our definition, remember, we can say let AB divided by B equal C. That implies that AB is equal to B times C. And again, what does C need to equal to make that true? Well, both sides have a B. How about C must equal to A for this to be true? So AB divided by B is equal to A. And you'll see that's exactly what we have. Now I used C, whereas this typed up answer used X instead. Does it matter what variable you pick? Not at all. We still got the same result. The answer was A. Now let's look at the next example. So I've got AB divided by A, and this time A is not equal to 0. You know why, right? Because we're not allowed to divide by 0. So again, we're going to let AB divided by A equal, let's let it be X this time so we're consistent with the typed up answer. That implies that AB is equal to A times X. Now notice there's already an A on both sides. Doesn't that mean that B must equal X? And it does. And so I could say that AB divided by A is equal to B. And that's my result. And you will see it typed up right there. Now I've reached my max. I've gone over my 30-minute mark, so I would like to come back for part 2 of section 5-2 and continue talking about multiplication, division, but specifically ordering integers, so less than, greater than, and order of operations.